This is a demonstration of a completely automated comparison of two different STR typing kits. The scenario is, for example, that you have a tendering process and you have been offered 2 or more kits and want to compare the characteristics of those kits. So I have opened up my R markdown file here, and here is the code. There are 2 ways to generate the result. The first option is to directly generate a file. It could be a HTML file, PDF, or a Word file. The second option opens up a graphical user interface where we can specify the parameters. For example, my name, the instrument IDs, the name of the kit and path to the files, and the name of the second kit and path to the data files. You can also put in options. For example, I have an option here to sort the tables in alphabetical orders by marker. Then we press the knit button to start the generation. And generating the report can take a while, depending on how much data it is to be analyzed and how complex calculations that you have. When it's finished, the result will open up in a viewer window where you can preview the result. Here you can scroll down your report, but you can also publish it online directly through this menu on RPad or some other destination. You can also open it within your browser. Here you can use your built-in browser functions, for example, to print this PDF. Is the title of the report, comparison of Fusion 6C and Sure ID 27. And the nice thing here is that we have used placeholders or constants for our kit names. So wherever in the report it says Fusion 6C and Sure ID, that comes from the constant. And that means if I get 2 different kits that I would like to compare, then I just have to update the names and the path to the files and then generate the analysis again. All the names switch to the new names throughout the report. And this report also, of course, have a generation date. It starts with some kit information with the number of markers for each kit, but also you can combine within your text, you can combine calculations. So here is a calculation of the number of overlapping markers between the 2 kits, and then it automatically lists the different marker names that is overlapping between the kits. And then comes a figure of the marker ranges for the different kits. After that, we have a section explaining the experimental design. And this analysis needs a number of negative non-template PCR controls to estimate the analytical threshold or the level of noise. And then we need some allelic ladders to determine the allele sizing precision. But also we need a lot of data from authentic samples. And here we have 85 authentic reference samples, which have been directly PCR amplified using the Fusion 6C and Sure ID 27 kit. We also need a reference dataset with known profiles that has been analyzed. Then we list the source data files for the Fusion kit and the Sure ID kit. We have the exact file names for the input files, the date and timestamp of the files. So we have full traceability of what data was analyzed to generate this report. Then we have a section R packages and operating systems that list STR-validator package version and the R version number, the platform, and the operating system. The first analysis is the analytical threshold, and we have some general information about the analytical threshold with links to the international guidelines. And the result is summarized in a two different tables, one-line tables, one for each kit. For example, here you have the global analytical threshold, and per dye, the blue, the green, yellow, red, and the purple dye. And the conclusion is that the Fusion 6C had the least noise with a global across dyes estimate of 25 RFU compared to 39 RFU for Shure ID27. Then there is a table of all the input files and the number of noise signals for each file. The next section is the allele sizing precision. Also here we have some general information and links to the international guidelines. And the result is summarized in this sentence here. The maximum size difference for Fusion 6C was 0.12 base pair, and for Shure ID27 it was 0.23 base pair. And the size difference of 1 corresponds to plus minus 0.5 base pair. And all the data is in the table below. And this is an interactive table, so this is really nice. You have buttons on top where you can copy the data. You can export as a comma-separated file, export to Excel, print as a PDF or to the printer. And all the headers here is clickable, and you can sort the table according to any header in a descending or ascending order. You can also type in text to sort the table. So for example here, if I click the size difference one time, I get the lowest value on top. And if I click it one more time, I get the largest value. So we can see that the marker D6S477 had the worst sizing precision. Then we have an interactive table with all the data. And we can easily see that it's between 0.15 plus minus 0.15 deviation from the mean. And in this plot we can hover a point to get the coordinates and also the marker name and the kit name. So this is very useful. If you want to verify an outlier, you can easily find out what sample it is, and you can go back to the EPG to check for artifacts or see that everything is correct. And if I click the series here, I can deselect the Shure ID27 to get only the Fusion 6C data. And now I can easily see that it is between plus minus 0.0. Here in this case, we can directly see what sample it came from, and we can go back and verify that it is correct. If I deselect the Shure ID27, we can easily see here that more than 75% of the heterozygote peak balance was more than 80%. So this is really good. Again, we have an interactive plot summarizing all the data. The next session is the profile balance. Here we have summed the peak heights in each marker, and then we have normalized each dye channel to the marker with the highest peak height. And what we can see is that for the Fusion kit, which is the top plot, we have a best amplification of the shortest markers, and we have a worse amplification of the longer markers. But for the Shure ID kit, this is not a clear trend, so here actually some of the longer markers amplify better than the shorter markers. And that's an interesting observation. Next we have the stutter ratio. And again, some general information about the stutter ratio and the link to the guidelines. The largest stutter ratio observed in Fusion 6C was 0.496, and in Shure ID27 it was 0.0386. Again, we have a table with all the data, in the type where -1 is the backward stutter and +1 is a forward stutter, we can drag these sliders to -1. So we only have the backward stutters. Then we can filter the kit to show only the Fusion kit and sort the table in ascending order. Now if I export this to Excel by clicking the button and opening Excel, now I have a nice table showing only the backward stutters for the Fusion 6C kit, sorted in order of the stutter ratio. So we can easily see that the Penta D have the lowest amount of stutters, and that D21 have the highest amount of stutters. Finally, we have the allele calling concordance. And as I said previously, we have 7 overlapping markers in these two kits. And the overall concordance was 99.5%. The result is summarized in the one-line table. 85 samples in total, 7 loci, and 1190 alleles analyzed. We found 6 discordances here, and the total concordance were 99.5%. And the observed discordances are shown in this table. So here we have a number of alleles that were called in the Sure ID kit, but were an off-ladder peak in the Fusion 6C kit. So I hope that this has given you some ideas of how you can use R Markdown to automate your workflow